Hi, year 11. In this tutorial, I'd like to go over or introduce you to hydraulics. Hydraulics are an extremely important area for engineering. And in year 11, we'll be just introducing them and giving you fairly simple questions on it. And so I'd like to start by going through page 71 of the workbook. And so you can see that a fluid refers to either a liquid or a gas, and the liquid is referring to hydraulics. So the liquids can't be compressed, whereas pneumatics refers to gases, and gases can be compressed, and that's what makes hydraulics much more accurate to work with. For example, if you had pneumatics in a crane, when the mass would be lifted and it stops, the hydraulic fluid won't compress, so you'll get an accurate stop. But if it was pneumatics and it had gas, it would bounce quite a bit because of the compression of the gas in the system. So they don't use pneumatics for things like cranes or earth-moving equipment. So pneumatics generally keep around 700 kilopascals pressure, and they're mainly used for hand tools with a compressor offering the pressure in the pneumatic line. And whereas hydraulics can work up to 40 plus megapascals, because, as I said, the liquid won't appreciably compress. Hydrostatic pressure, we'll just go through a few basics, is the pressure at a given depth of a fluid, and the pressure as you know, varies with the depth of the fluid, and you can get the hydrostatic pressure at any depth by multiplying the density of the fluid, which is in kilograms per cubic meter, gravitational acceleration, and the depth or the height that the object is at. If you want to add the pressure applied to the closed system, like it might be a hydraulic cylinder, a piston in a cylinder, or it could just be the atmospheric pressure on the surface, you've got to add the added pressure there, which is P0. Make sure that you know that pressure is evenly transmitted throughout a liquid at the constant height. We don't worry about the difference in height because most of the hydraulic systems that are used in engineering are at the same height above sea level, so the height doesn't come into it. And they're closed systems. And also make sure that you know that the force operated within a closed system will always act at 90 degrees to the walls of the system. As you know, hydrostatic pressure varies with depth, and the difference in the depth of a submerged object, of the pressure between the top of the object and the pressure below the object, creates a force called a buoyancy. And the force of buoyancy is generally equal to the volume of the submerged object if it was in the liquid. If the volume of the liquid is weighed, that force, the weight force of that volume, would equal the buoyancy if it's submerged. Make sure you know Pascal's principle, that pressure is applied to a confined liquid is transmitted equally throughout the liquid. And I'll just show you some applications of hydraulics, and then we'll go through this method that I've used so that you can remember the three important equations of hydraulics. Let's have a look at this bulldozer. So this is, as you know, is a bulldozer. You've got the final drive wheel above all the dirt. They've pushed the final drive wheel up above the dirt because the dirt is quite abrasive and it wears a lot of the mechanical components. And as you can see here, these are the hydraulic systems cylinders that we're talking about. There's a hydraulic cylinder here, which tilts the blade. There's a hydraulic cylinder here that does the gouge at the back. And you've got this hydraulic pair of cylinders here, which lift the blade. And it's really important to position these hydraulic cylinders in the correct orientation, because there's one direction of a hydraulic cylinder that is more powerful than the other direction. And by the time we finish this, I'd like to explain that, but you have a think about it during this talk. And just think of why a hydraulic cylinder with the piston there would have a strong and a weak direction. As you can see, the strong direction is going down here, pushing the blade into the ground. The weak direction will be lifting the blade up because it requires a lot less force. Let's have a look at an excavator here. You can see you've got all these hydraulic cylinders here, and they call them actuators. An actuator is just an engineering term for something that gives movement from an input. And so this hydraulic cylinder up here, look at the way it's been arranged. It's been arranged so that the strong direction is pushing it out so that the bucket can actually dig into the ground. This one here is the strong direction is going downwards so that it can lift the mass of dirt or whatever that's in the bucket. And obviously the strong direction is pushing that up there so that the boom, which is quite heavy, and the mass in the bucket will have obviously the strong direction of these cylinders pushing up there. So let's just get back and have a look at these formulas that we're looking at. So hydraulic devices make use of Pascal's principle. That means the pressures on the input side are the same as the pressure on the output side. And you'll see a setup like this. So here we have the input, and that there is the output. And remember, the pressure remains constant throughout the hydraulic fluid. And you can see if you've used a hydraulic jack, when you're applying a force to the lever, the input lever, you have to move that lever a lot more than the car is lifting from the output. And that's because of the conservation of energy. So let's have a look at this first equation. So we've got pressure out is equal to pressure in, and that's according to Pascal's principle. Now, what I've done here, I've used big F to be the big pressure and the big force, and the small f to be the small force. So obviously with the input, you want to have a small force there, and you want to have a big force coming out here. So you can see here that I've used big F for the big load force and small f for the small input force. And I've done the same with the distance. So the distance in here, you'll be pumping away and the input will be going a lot further than the output. So I've put a big D for the big distance there and a little d for the small distance that the output piston is moving. Okay, so if you've got, and I've done that here, the same with area. So the big area here will be this area here, the area of the output piston, and the small area will be of this input piston there. Now, pressure equals force over area. So you've got, and because the pressure is constant, so you've got the force out over the area out has to equal the force in over the area in. And notice that I've put the big force out, the big area out, which is this here, big area and the big force. And we've got the small force in this little f and the small area there, okay? And you see the difference in the area there. This one has got a piston of 540. This one here's got a piston of 520. So that's the first equation using Pascal's principle, using that pressure is constant throughout the hydraulic system. The second equation I want you to remember is the conservation of energy. Assuming that the hydraulic system is 100% efficient, which it never is. It's very efficient. It's probably fairly similar to an electric motor, around about 85, maybe 90% efficient. And so what we did last week was energy. Energy is equivalent to the work done on an object. So that means work in has to work out, has to equal work out. And that's because of the conservation of energy. And you know that work is force times displacement. And so we've got work in. So we've got a small force in multiplied by a big distance in. You can see that you move 4 times, and we'll see this in a minute. You move the input force 4 times to that of the output force. And so this is the input side, and that's the output side. So you have a big F out and a small distance out. So let's apply that to this hydraulic system here. This is a similar hydraulic system. I haven't shown a valve here. You'll have a one-way valve there. And if anyone of you have used one of those little bottle jacks, you know that you screw a screw to keep the valve open, or then you unscrew it and it will close it or open it depending on the jack. So let's work out what the force out here will be given all of this information here. So the pressure is constant, so therefore big F out over big A out, that's this side here, is equal to the small force in over the small area in. So here we have the small force and the small area. Don't forget that D is distance, and we use that for this one here. Okay, so don't forget we're using this formula here. And so you just substitute and you can see that the force out will be 400 with you putting 100 Newton force in there. But the problem is, if you apply work in equals work out, this formula here, which is this one here, you'll get the distance in will equal 4 times the distance out. And so you only apply 1/4 of the force, and you'll get 400 newtons. You get 4 times the force out, but you've got to move the input force 4 times the distance that the output force moves. And so really you get nothing for nothing. You have to apply this because human muscle is very weak. And we need machines like this to help us. And it's the same thing with disc brakes. If you didn't have a brake booster, which I'll go through in a minute, on your car, and I hope you've lifted the bonnet and had a look what a brake booster is and what it does. Now, if you didn't have a brake booster, you wouldn't be able to apply enough force to the pedal to stop the car if you've got disc brakes on the car. Drum brakes are different because they have a self-energizing leading shoe on them, and you don't need a brake booster for drum brakes. When I was your age, all cars had drum brakes and brake boosters didn't exist. But as soon as disc brakes started coming in, you had to have some means of surveying the force, allowing you to apply less force, but the brake booster will boost up the force. Okay, so I hope you've got that, and that's as a result of the conservation of energy. Now let's have a look at velocity ratio. Velocity ratio is the distance that the effort moves over the distance the load moves. It actually is defined by this. So velocity ratio is equal to the velocity of the effort over the velocity of the load. But velocity of the effort is the distance that the effort moves over time. And the velocity of the load is the distance the load moves over time. So you invert it and multiply. And so you get time there and distance that the load moves. And your time cancels because the effort operates at the same time the load does. And so we get a velocity ratio of the distance that the effort moves over the distance that the load moves. Okay, so that's velocity ratio. Look, if you have a gear, a small gear here and a big gear there, and this is the driver, and that is the follower. These are gears. Let's just say that has a diameter of 100. And this has a diameter of 200. You know from your bike that this one will go much faster than that. And where the velocity ratio is the velocity ratio of how fast this is going compared to that. So the distance that the effort moves, because you know this is going to go faster than that, if you just put that over that, you'll get a half, and that's less than 1. But you know that this has to go much faster than that. And so therefore, you do the inverse, which I've explained in the relevant section in this book. So the velocity ratio equals the inverse of the two. So you go to the follower. It's the distance that the follower is, or the diameter, or the circumference over the diameter, radius, or circumference of the driver. And so you get a velocity ratio of 2. So this is going twice as fast as that. So that's what velocity ratio is. A brief revision of velocity ratio. Now let's have a look at a velocity ratio of a hydraulic system. Now I don't want you to have to go through all this with this. I want you to remember this, and this will not be on your formula sheet because it's a derived formula. So let's have a look at it. So you know that when you're applying a force to this, the volume of fluid that actually moves, and remember the fluid doesn't move, it's just a transfer of force. You don't get fluid actually moving, it's just a transfer of force through it because it's a closed system. So, but the volume of the fluid that actually is transposed from here to over here will be equal pi. This is on the input side, so it'll be pi d squared on 4. Remember, pi d squared on 4 is the same as pi r squared. It's the area multiplied by the distance. So you have this input piston moving a certain volume of fluid, and that fluid goes over and takes the place over here. And so the volume of the fluid from here is exactly the same as the volume of the fluid over there. So the volume of the fluid is area times distance, just like the area of a cylinder. And this is the input, so it's big D. So it's big D. And then on the other side, this is the area of the output piston. So that's going to be a big area multiplied by a small distance. And they'll be equal. The volumes will be equal. Now we have to arrange this as distance that the effort moves over the distance that the load moves. Now, DE is the effort and D out is the load there. And so we've got distance in, there's distance in, distance out, equals, they all cancel, which equals big phi squared over little phi squared. Since velocity ratio is equal to distance of the effort over the distance of the load, which we've got there, which is there, then the velocity ratio will equal big phi squared over little phi squared. And I want you to remember that because it will save you heaps of trouble. So the velocity ratio of a hydraulic system, and you'll be given the radius of the pistons or the area of the pistons or the diameter of the pistons or the circumference of the pistons will equal big phi squared. Now, big phi is the diameter of that over little phi squared. And the way to remember it is the big bubble floats on top. Okay, and remember, you won't be given that in the formula sheet. And that's all you have to know about hydraulic systems. So let's have a look. Hydraulic systems are extremely efficient. Like when I was your age, there weren't very many hydraulic systems around. They used cables and mechanical systems. But hydraulic systems are cleaner, they're easier to adjust, they're much more powerful, and that's why they're basically ubiquitous. They're used widely in all areas of industry, and I want you to keep your eye out and just have a look at all the hydraulic cylinders and that you see in virtually every mechanical apparatus. So let's have a look at this here. This is a circuit for a hydraulic cylinder and motor. This is for a hydraulic cylinder. So you've got a big reservoir of hydraulic fluid, and you've got a super powerful pump. And the pumps are really small but very powerful. And you have a look at a concrete truck agitator, huge, could have 10 tons of concrete in it, and have a look at the little motor that's driving it. It's right at the end, and you'll see hydraulic hoses going into it, and it's a very small motor, very efficient. So that's the pump there. And sorry, this is the motor here, but the motor is very similar to the pump. So this is just driving the hydraulic cylinders here. There's the levers that operates the valves to allow the hydraulic fluid to go in one. This is called a double acting hydraulic cylinder. So when you want the ram to go out, the hydraulic fluid goes in there and then it goes out there. And when you want the hydraulic ram to go in, you change the lever and the fluid changes and goes in here and drives the ram down. This is a hydraulic motor. This is the one that drives those agitators on the concrete truck. So you've got everything set up the same, and you've got a really efficient method of driving a pump. You can see this bulldozer, for example, here could be 75 tons, and they've got a little hydraulic motor in there driving the final drive. But it's really good to have a look at a concrete agitator and just have a look at the end and just see the little motor that's driving it. They're very efficient motors. This is a typical hydraulic cylinder. So this is a fairly small one. So there's the piston, and you can see, or you've got these piston seals. When I see you, I'll be bringing one up to show you how it works, and I'll just quickly show you how they work. So you've got the seal that's like this, and it is tapered. And so this is the cylinder there, and you've got your hydraulic fluid all over here. And so when you've got a massive amount of pressure in here, not only is it pushing this seal, and this is a neoprene seal, it's pushing at 90 degrees to all surfaces. And so this is tapered so that when the force pushes up against the angle of the seal, it's forcing the seal up against the wall so the higher the pressure in here, the better the seal. And that's a sort of a self-surveying effect to get the seals very good, and they won't leak. When you see seals leaking, you've just got to replace them. And so here's this is the barrel of the cylinder, and that's generally made from stainless steel. And this is the piston here with all the seals on it. This is a wiper here that wipes away any dust that's collected there. And this is the piston rod here. And you can see that the piston rod is very highly finished. It's a chrome, and you don't want any pickup on that. You want it to be nice and smooth so that doesn't damage any of these seals down here. Let's just have a look at the advantages of hydraulic systems. Equal forces applied to each output cylinder, higher efficiency than other systems, less maintenance and more reliable because hydraulic systems are self-lubricating, resulting in less wear. So the hydraulic fluid is lubricating the moving parts. Low inertia of moving parts allows hydraulic systems to start and stop quickly, resulting in greater sensitivity and more precision. And that's what I was telling you about with cranes. It will not bounce up and down because the hydraulic fluid won't compress. Now, one disadvantage, I was telling you about the brake booster. I hope you've all seen it. So this is the brake master cylinder here. This is the brake booster here. And this is the brake pedal inside the car. And this is how it actually works. So when you put your foot on the brake, it opens up a valve here, just somewhere on the outside of the brake booster. And when it opens up a valve, this valve is connected to the inlet manifold of the engine where the air is rushing in. And when you buy Bernoulli, you'll have a low pressure area there. And so when you open up this valve, when you put your foot on the brake here, it moves this diaphragm. It sucks this diaphragm along and it helps you with the movement of this piston, which pushes the hydraulic fluid into the wheel cylinders, and these are the disc brake pads there. And so that's how a brake booster works. So you're using the air that's rushing in the inlet manifold to reduce the pressure in a line, I haven't drawn it here, connected to the outside of the brake booster, and that will drag that diaphragm along and help you with the force on your brake pedal. Okay, I hope that's okay, and let me know if you need any further help with this, and I'll just stay on if anyone wants to ask me any questions. Okay, thanks for logging on, and I'll do this recording. I'll put it on the emails tomorrow.